Good morning, everyone. So today we are going to discuss about the optical isomers. So in previous class we have discussed about geometrical isomers. So these optical isomers and geometrical isomers comes under stereoisomers. So what are stereoisomers? They have same molecular formula, same bond connectivity, but these molecule differs in the orientation of groups in spatial. Okay, in space or in 3D or given space, if the groups are oriented in different manner and having same bond connectivity and same molecular formula, then such isomers are known as stereoisomers. Next, see optical isomers. So optical isomers which exhibit optical activity is referred as they rotate plane polarizer light in either right hand side or left hand side. If any molecule which rotate PPL or plane polarized light towards right hand side, then that will be designated as dextro, you know, dextro, or else small d. If any molecule which rotates the plane polarized light into left hand side by some degree, that is known as LEVO, or that is also designated as small a. Okay, so what is plane polarized light? So when in ordinary light, the light particles, or we can say energy particles or energy packets, those photons are vibrated in all direction. When that ordinary light is passed through a Nicol prism, then what happens? These all light particles will vibrate or orient in one direction or single direction. Such light is known as plane polarized light. Okay, so so this is an experimental procedure. So this experimental procedure generally we carried out by using polarimeter. Okay, so polarimeter is a polarimeter. It consists of a source, that is ordinary light, source of ordinary light, and that radiation of ordinary light is passed through a Nicol prism. Second object is Nicol prism, so that will convert this ordinary light into plane polarized light. Next, this plane polarized light is passed through a polarimetry tube. So polarimetry tube or a tube. So that tube contains a dilute solution of our examining compound or analyte, so which is under examination. So whose optical activity to be determined, that will be taken in the tube, that to be in dilute solution. Dilute manner means concentration of that solution should be very very less. So when PPL light is passed through the tube, so actually in the tube what we have, our isomer or optical isomer or compound, so it will interact with that plane polarizer light, and it rotate that PPL light in either direction, in the right hand side or towards left hand side with some degree, that is known as theta. So if that plane polarizer light is rotated towards right hand side with theta degree, then that is designated as a dextro, or we can say dextro molecule. For example, glucose is also known as dextrose. Why? Because this glucose solution, dilute solution of glucose, will rotate PPL light into right hand side. That's why that glucose is also known as dextrose. And next one, one more possibility is if that PPL light can be rotated into left hand side with theta degree, then that isomer is designated as LEVO. For example, honey is a LEVO rotatory, or else our fructose is a LEVO rotatory. Okay, so now come to this coordination compound. In that coordination compounds, we are studying the optical activity of coordination number 4 and coordination number 6. In coordination number 4, we have two geometries. One is tetrahedral geometry and second one is plane polar geometry. Out of these two geometries, only tetrahedral geometry will exhibit this optical activity, or gives optical isomers, whereas octahedral or coordination X6 compound, that will give uh, optical isomers. Okay, next. These optical isomers again are mirror images, but those mirror images are not superimposable. Then that set are those are called as enantiomers. So again, what? If those optical isomers means which will rotate PPL light in either direction. So to rotate the PPL light in either direction, the basic criteria is that the molecule should have at least one chiral center. What is chiral center? So in organic chemistry, you have studied about chiral center. What is chiral center? If any carbon which is bonded or connected to four different atoms or groups, then that carbon is known as chiral carbon, or we can say chiral center. And that molecule which has chiral carbon is considered as a chiral molecule. So here in this case also, our central metal atom should have chirality. So that should have chirality. Okay, next. So here the mirror images not be superimposed on each other. Those are known as enantiomers. What are diastereomers? Another set is diastereomer. Those are non-mirror images and non-superimposable. So such sets are known as diastereomer. So to be as an enantiomer or to be as a diastereomer, the complex compound should have at least one chiral center. At that time only this complex compound can exhibit optical isomers. Whereas in plain square planar compound, so that molecule may possess some symmetry elements like axis of plane of symmetry or rotation of symmetry or alternative symmetry elements. So that's why that will not exhibit any optical isomerism. Okay, so next, now let's see the optical isomerism of coordination number 4 compounds. So in that coordination number of 4 compounds, we have two geometries. One is square planar geometry and second one is tetrahedral geometry. So out of these two, only which will exhibit optical isomerism, only tetrahedral geometry or tetrahedral complex compounds will exhibit optical isomerism, whereas plain square planar compounds do not exhibit optical isomerism. So in this coordination number 4, we have only one example, only one molecule can exhibit optical isomerism. So that is this one, uh, the square planar complex, chiral isomers of square planar complex. Okay, next here see, this is. So optical isomerism, so coordination number 6 compounds, here we are looking at 6, but example is this is 4, this is tetrahedral complex, tetrahedral molecule. So here see, on your left hand side, in this first example, on your left hand side, again I am increasing the size. Okay, see, this is. So on left hand side here, in this coordination number 4 compound, we have three types of bonds. So these two, first two are in plane bonds, so which are represented in normal mode. So these are, this bond and this bond is in plane bond, and this one is above the plane and this one is below the plane. In first isomer, in first optical isomer, these two above the plane and below the plane is shown towards left hand side, and this is a mirror image. Optical enantiomers means mirror images, non-superimposable mirror images. And if you take the mirror image of this, then these the two bonds which are oriented in left hand side in first compound, so what happened, they are changed to right hand side. So that's why this is one optical isomer. Okay, so example, here we have cobalt NH3Cl Bri. So here he has taken four different monodentate ligands. Generally we can represent this molecule as MABCD. Okay, it is a tetrahedral molecule with four different groups bonded to the cobalt. So has two non-superimposable mirror images. These are. Next, so we have only one optical isomer in tetrahedral compound. And next, if you come look at octahedral 6, the octahedral 6, sorry, coordination number 6, or we can say octahedral complex. Here, this is the geometry of octahedral compound. So if you look at these bonds, these are the in plane bonds, and these are the one is above the plane, second one is below the plane. AF. So AF will be remained same, and here ED oriented on right hand side in first molecule, and if in the mirror image those are in left hand side. If you so place this one on this, it may not be superimposable. So that's why these two are again what, enantiomers. Okay, and this three, this here we have M, A, B, C, D, E, F. Though that means all six monodentate ligands are different. Okay. Next, stereochemistry. Now look at another example. Ma5B type. Ma5B B. So that means all six are monodentate. Out of six, 5 are same, one is different. So this is the geometry, optical isomerism. So here see, Cl is oriented in on left hand side in first enantiomer, and in mirror image that is oriented on right hand side. Then these two are mirror images and unsuperimposable, so that we can say these are enantiomers. And next example here, this is up to M A B C D E F, and this is M A 5 B. Or you can take number of examples are M A 4 B 2, also M A 3 B 3, or M A 2 B 2 C 2, like that. Okay. So now mixed complex compound, so which has symmetrical bidentate ligand and monodentate ligand. So capital AA, which is present in parenthesis, it is symmetrical bidentate ligand, and two similar monodentate ligands, and two another similar monodentate ligands. So it can give optical geometrical isomers also. So, but in the case of cis, it is optically inactive. Why? Because cis form may have some symmetry elements, so that's why that cis form do not exhibit optical isomerism. Whereas transform can, sorry, transform is optically inactive. This is transform. Sorry, transforms are optically inactive, whereas cis forms are optically active. This is cis form. Why? Because here see similar groups on same side. Okay, these two. This is first orientation, and this is its second orientation, and these two can exhibit optical isomerism. If you take the mirror image of this one, then what happens? This ethylene diamine orients are comes on right hand side. So here see he generated these two by changing the displacing the monodentate ligand position, and one two. This is another two cis isomers. Here he changed the orientation or placement of bidentate ligand. Okay, so NH3 on same side, Cl on same side. Okay, now look at this one. This is transform Ma2 B2, MAA2 and A2. So two symmetrical bidentate ligands, and one remaining two are monodentate ligands. So this is which form? And this is transform, and again here see it transform. It is optically inactive. Why? Because we can bisect into two equal halves, so that's why it is optically inactive. And moreover, these are mirror images, is it not? These are mirror images. And this is C, this is cis form, and this cis form is optically active. Why? Because these two are not mirror images, so that's why cis form is optically active, whereas transform is optically inactive. And next, come to another example of MAA2 AB. So here also symmetrical bidentate ligand, two bidentate ligands, and monodentate ligands, two are different. So similar to this. So it is a trans and optically active. Why? Because non-superimposable mirror images, and here also we can say as this is this is trans and this is cis. Okay, so trans with respect to chlorine and ammonia, chlorine and ammonia. So here chlorine and ammonia are presented, are oriented on same side, that's why it is cis, and this is with respect to chlorine and ammonia, this is trans, and these two are optically active, and this is, so see, this is cis form and this is trans form. Okay, both are optically active. And next one is MAA3. So here this complex compound consists of all bidentate ligands. Here we don't have any monodentate ligand, and all are symmetrical bidentate ligands. So it is optically active. Okay, so this is about the optical isomerism. So with this we have completed um, isomerism. And square planar, it is a square planar tetrahedral compound. In this square planar, it is the only optically active compound. This optical activity is attributed due to the presence of chiral carbon of ligand. Okay, here this central metal atom is not ligand in nature, the chiral in nature, but whereas this connected carbons, these carbons are optically active. Okay. Those are chiral carbons. So here see, here we have this is chiral carbon. Why? Because this has connected to four different groups, 1, 2, 3, 4. This is also chiral carbon. Okay, so this chiral carbon, due to this chiral carbon of ligand, that imparts optical activity to the square complex. But actually, the central metal atom is not a chiral in nature, so it is the only tetrahedral molecule which exhibit a square planar molecule which exhibit optical isomerism. Okay. So in case of tetrahedral, M, A, B, C, D, so R4, and in case of coordination number 6 are octahedral compounds, we have different combinations. M, A, B, C, D, E, F, one combination, M, A, F, I, B, one combination in case of all monodentate ligands. And next, this is mixture. So mixture means this complex compound contains symmetrical bidentate as well as monodentate ligands. In this case, C trans isomer is optically inactive, whereas cis isomers are optically active. So all these are cis forms. And next, this is another type that is MAA2A2. So this it has two bidentate symmetrical bidentate ligands, and here see this is transform. It is optically inactive because it has plane of symmetry as well as these two are mirror images. So this is optically inactive, and this is cis form and it is optically active. Okay, next one MAA2AB. So here also with respect to Cl and ammonia, so here our reference groups are chlorine and ammonia. With respect to these two, this is a trans, and if these two groups orient on same side, then that is cis, and both are optically active. And next and third one, MAA3, it is it consists of all symmetrical bidentate ligands, and it is also optically active. It is dextro and it is levo. Levo means it will rotate plane polarized light towards right hand side, and it will rotate plane polarized light towards left hand side. Okay, so I hope you have understood this. So with this we have completed about coordination compounds. In that coordination compound, so far we have discussed about nomenclature, then calculation of oxidation state of central metal atom, and then we have studied about theories, three theories. First one is Wagner theory, second one is effective atomic number theory, or it is also known as EAN theory, and that theory is proposed by Sedgwick, so that's why that is also known as Sedgwick theory. And then we have studied about valency bond theory, VBT, so that is proposed by Hunds, and this isomerism. So extension to that VBT. Why? Because VBT, according to VBT, the bond present between metal and ligand is a coordinate covalent bond, and this coordinate covalent bond is a directional bond. So the compounds are the molecule which has the directional bond. They can exhibit isomerism. So again, isomerism two types on the basis of connectivity. If the compounds, two compounds have same molecular formula but a different connectivity, such are known as constitutional or structural isomers. Again, structural isomers are four types: hydrated, ionizational, linkage, and coordination. Next, to come to stereoisomers, which have same molecular formula as well as same bond connectivity, but they differ in orientation of groups in space. So again, those are two types on the basis of PPL light or optical activity, mirror image nature. So again, those are, if non-mirror images, then we can say optical isomers. If they are mirror images, then we can say geometrical isomers. Okay, geometrical isomers again two types, cis and trans. If two similar groups are two reference groups are two similar groups who orients on same side, then that conformation or that geometry is known as cis. If two similar groups or two reference groups are oriented to 180 degrees or oriented in opposite direction, then that is known as trans. Next, come to optical activity. So what is optical activity and what is the basic criteria to exhibit optical activity? The basic criteria to exhibit optical activity is to possess at least one chiral center in that complex or molecule. So the chiral means in general organic chemistry we have studied that chiral carbon. So what is chiral carbon? The chiral carbon which is surrounded to four different groups or atoms. Here also in this complex compound, our central metal atom, which connect to different atoms, that is considered as chiral. So here, if the complex compound which rotates plane polarized light towards the right hand side, then that is known as dextro. If the complex compound which rotates plane polarized light towards left hand side, then that is designated LEVO. So dextro, small d, LEVO, small l. Next, optical isomers are two types on the basis of superimposability of mirror images. And mirror images and non-superimposable are known as enantiomers, and non-mirror images and non-superimposable are known as diastereomers. Okay. Next, again, we have now we need to study the optical activity or geometrical activity of two complex compounds, two types of complex compound, coordination number of 4 and coordination number of 6. But in coordination number of 4, we have two different geometries, different shapes, or different hybridization. One is sp3 that gives a tetrahedral geometry, and the dsp2 that will give square planar. In geometrical isomerism, tetrahedral do not exhibit geometrical isomerism, whereas square planar can exhibit geometrical isomerism. In case of optical activity, only tetrahedral geometry can exhibit optical activity, whereas square planar do not. But we have one exception. Just now we have seen that exception. What is that? A square planar compound can also exhibit geometrical optical isomerism. That optical isomerism arises due to the presence of chiral carbon in ligand. Okay, so this is about energy isomerism. And in this topic, so the crucial or heart of this coordination compound are in second semester. Next semester we will discuss about, we will learn about CFT, magnetic properties or color properties, etc. Or Jobs method, or we can say complexation. All these are applications. So in the whole lesson, the heart or major part is to know the how to calculate the oxidation state of central metal atom. So if we able to know, or if we able to calculate the oxidation state correctly, then we can answer nomenclature, Werner theory, EAN theory, valency bond theory, CFT, and properties like color property, magnetism, etc., etc. Okay, so again, I am requesting you all, please be thorough in calculation of oxidation state. Okay, and I will provide this material in our Google Classroom. Okay, so I hope you have understood this. Thank you very much.